Hey everyone, this is a video reviewing all of the solutions for the homework for section 1.3, including the textbook work as well. On the first worksheet question, we're taking the limit of a complex fraction, and anytime we're taking limits, we want to be aware of domain restrictions. So if we take a look at the denominator of the complex fraction, x plus 7, that would give us a domain restriction of -7, because when you set x plus 7 equal to 0 and you solve it, we discover x equals -7 will make that denominator 0. So we would say x cannot equal -7. Essentially what this means for us is that we have more work to do, okay? We can't use direct substitution and just plug in -7 for x to find the limit. When you're dealing with a complex fraction and finding limits, we need to find the least common denominator of all of the fractions, which in this case, we'll use the denominators x minus 3 and x plus 2. And the product of those two factors will be our LCD. Okay, and what we want to do in this case is take and multiply every single part of our complex fraction by this LCD. Okay, so what it looks like in the numerator, well, first let's just write it out so we remember that we're going to multiply both the numerator and the denominator by x minus 3, x plus 2. Okay, so we're going to multiply that fraction 2 over x minus 3 by the LCD. We're going to multiply minus 1 over x plus 2 by the LCD. And we even have to multiply the denominator, x plus 7, by the LCD. Well, one thing to keep in mind is that we need to keep it in limit notation. So the limit as x approaches -7. And I'm going to write everything out. Remember, you can shortcut it if you can see what is going to reduce when you multiply by the LCD. So that should be x minus 3. And then x plus 2. You can put it over 1 minus 1 over x plus 2 times our LCD, x minus 3, x plus 2 over 1, all over x plus 7 times x minus 3 times x plus 2. Okay, so we are going to keep that limit notation. So limit as x approaches -7. And we are going to start reducing. So right here, we can reduce by dividing out the x minus 3's. And notice that we're left with a 2 and x plus 2. All right, I've warned you about this part right here, that minus sign, okay? That usually is where most mistakes happen. All right, so the next multiplication we're going to do is the 1 over x plus 2 times the LCD. And so it's the x plus 2's that divide. And here's where we need to be careful. We are left with an x minus 3. Keep it in parentheses. Again, because of this negative, we're going to distribute that to both terms. So the signs are going to change. In the denominator, I want you to keep it as x plus 7 times x minus 3 times x plus 2. All right, don't multiply those together. Okay, let's start simplifying the numerator. And we'll distribute that 2, and we get 2x plus 4. Distribute the negative, so we end up with -1x, or just -x. -1 times -3 is +4. All being divided by x plus 7 times x minus, sorry, that should be x plus 3. All divided by x plus 7 times x minus 3 times x plus 2. Okay, keep that limit notation at least one more time. So limit as x approaches -7. Now combine like terms. 2x minus x is 1x. 4 plus 3 is 7. And notice how we have an x plus 7 in the numerator, and we have x plus 7 in the denominator as well. So those are going to divide, and that is removing the discontinuity. So we're removing the issue. And what we had happen when we would try to plug in -7 before, and it would be undefined. Well, now we've removed that discontinuity. So let me give myself a little more space here. Okay, so we divided out those x plus 7s, so now we have the limit as x approaches -7 of 1, because we do have this 1 in the numerator, over x minus 3 times x plus 2. Okay, now you're ready to do your direct substitution. Now it shouldn't be an issue to plug in -7. So we drop the limit notation, and we have 1 over -7 minus 3 times the quantity -7 plus 2. And just do your math carefully. So 1 over -10, because -7 minus -7 minus 3 is -10. And then in the other set of parentheses, -7 plus 2 is -5. So our final answer is 1 over 50. And leave it as a fraction, no decimals, okay? Okay, and the next two from the worksheet, we have trig. So one thing we want to do is take and plug in what our limit is approaching, our x value. So we're finding the limit as x approaches pi over 4 for the secant of 2x. So let's see what happens. We have the secant of 2 times pi over 4, which would turn into the secant of pi over 2. Okay. Now you have to take into consideration the graph of a secant function. And I know we spent some time graphing sine, cosine, secant, cosecant, tangent, cotangent. And remember that secant is the reciprocal of cosine. So I'm hopeful that you're able to graph a cosine function graph. So we want to go out to 2 pi, split it in half, and we get pi. Split each of those in half, we get pi over 2, and 3 pi over 2. All right, cosine goes up to +1 and down to -1, right, for the amplitude. Cosine starts at +1, comes down through the x-axis at pi over 2, meaning the cosine of pi over 2 would be 0. Cosine of 180 degrees, or pi radians, is -1. Then it starts to come back up, and at 2 pi we're at +1. Okay, so that's the cosine graph. Now I'm graphing this first to help you graph the secant function, the reciprocal. Okay, so secant, again, is going to be the reciprocal of sine. The first thing that you should do is come in and take a look at the graph, and look at the graph of cosine, and look for where cosine is equal to 0. Wherever cosine is equal to 0, secant would be undefined. Okay, so those would become asymptotes for the secant graph. Now if I go to graph the secant function, remember that it goes away from cosine and towards those asymptotes. Okay, so I'm graphing the secant function in green. All right, we want to look at the secant of pi over 2 radians. So check out what's happening at pi over 2. And what I notice in there is that on the left-hand side, it's approaching positive infinity. And then on the right-hand side, it's approaching negative infinity. When the graph is approaching two different infinities, at the point where we're trying to find the limit, we say the limit does not exist, DNE. Okay, so you do need to be able to graph your basic trig functions, sine, cosine, and then secant and cosecant. But remember, if you can graph sine and cosine, it should be pretty easy for you to get the secant and cosecant graphs done. Right? So again, this is a DNE because it's approaching two different infinities. Okay, so for the next one, we're going to take a look at what happens at cotangent. So it's the limit as x approaches negative 4 pi of the cotangent of 3x. So let's take a look at this as the cotangent of 3 times negative 4 pi, or the cotangent of negative 12 pi. All right, so cotangent. If we go to graph this one, and this one you should practice a little bit more before the quiz. So here's pi and 2 pi. Okay. You may find it helpful to first think of like tangent and think of where tangent crosses the x-axis. But cotangent and tangent function, I always think of it like, oh, it goes this way, kind of swoops down, rises to the right. Cotangent falls to the right. It goes in the opposite direction. There are asymptotes for cotangent at every multiple of pi, both odd and even multiples of pi. So at 0 radians, there'll be an asymptote. At pi radians, asymptote. 2 pi radians, asymptote. For cotangent, it crosses at pi over 2, crosses the x-axis at pi over 2, and at 3 pi over 2. So cotangent of 90 degrees, say, is 0. Cotangent of 270 is also 0. So your cotangent function is going to come in this way. That's what I mean by falling to the right. So it swoops down this way, falls to the right. All right. Now, I know we're finding the cotangent at negative 12 pi, but look at the behavior of the graph at every multiple of pi. For instance, at 1 pi, on the left-hand side, we're approaching negative infinity. On the right-hand side, we're approaching positive infinity. Right? This is the behavior that is going to happen at every multiple of pi. So we would say our limit does not exist. And it's for the same reason as number 2. We're approaching two different infinities. All right, next let's take a look at the problems from the textbook. All right, in the first group of problems, like in the 11 through 21 on, we have a whole series of questions that can be done just by direct substitution. And there are a few reasons for that. In number 11, we're taking a look at the limit as x approaches negative 3 of a polynomial. So since this is continuous, there are no breaks, holes, or anything. We're just going to use direct substitution. So take and plug in your negative 3. So do 2 times negative 3 squared plus 4 times negative 3 plus 1. And just be careful with your math. Of 2 times 9 minus 12 plus 1, or 18 minus 12 plus 1, which gives us a limit of positive 7. Again, I know I can use direct substitution because it's a continuous polynomial. It's a quadratic, so there are no breaks, holes, no asymptotes in it. Okay. In other words, no domain restrictions either. Number 13, a rational function will have a domain restriction. That domain restriction in this case is x is not equal to 0, but we're not finding the limit at 0, so we can just plug that 2 in, and there's our limit, 1/2. Okay, number 15, there are no domain restrictions to number 15, even though it's rational. X squared plus 4, if you set it equal to 0 and you solved, you would end up with imaginary numbers. So again, there are no domain restrictions. So we are ready to just plug in positive 1 and do the math out there. 1 minus 3 divided by 1 squared plus 4. So you end up with negative 2 over 1 plus 4, or negative 2/5. And just keep your answers as fractions, please. All right, number 17, notice that we're finding the limit as x approaches 7. 7 will not make this denominator equal to 0 because we've got the square root of x plus 2, so we're going to be taking the square root of 7 plus 2, which will be a positive 3. So we're ready to just do direct substitution. So do 5 times 7 over the square root of 7 plus 2. 5 times 7 is 35. That would be over the square root of 9. So we end up with 35 over 3, final answer. And you can just leave it as that improper fraction. All right, so for number 19, that x plus 1 inside the radical will have to be greater than or equal to 0. So as long as x is greater than or equal to negative 1, we can find the limit. We're finding the limit as x approaches positive 3. So go ahead and plug it in. So the square root of 3 plus 1 gives me the square root of 4, which is 2. All right, number 21, we have a continuous function again. This is a parabola. So there are no domain restrictions on a parabola. Its domain is the set of all real numbers. So since there are no domain restrictions, go ahead and plug your number in for some direct substitution. So negative 4 plus 3, quantity squared, gives us negative 1 squared, and notice it's in parentheses being squared. So final answer will be positive 1, because it's negative 1 times negative 1. Okay, so all of those, we were able to do direct substitution. It's not a bad thing to try first, but remember to watch out for situations that give you 0 over 0. If that happens, then you know that you have something to do to remove the discontinuity. All right, number 26, part A, we're finding the limit as x approaches 4 for f of x. And I notice that f of x is just an equation of a parabola. So it's a continuous function, no restrictions on the domain. So if we just go ahead and plug in 4, we can drop that limit notation and do 2 times 4 squared minus 3 times 4 plus 1, or 2 times 16 minus 12 plus 1, or 32 minus 12 plus 1, which will give us 21. Okay. For the second function, g of x being the cube root, it's an odd root, meaning that it's okay if we end up with a negative number inside the radical. It's okay if we end up with a positive number inside the radical. So again, it's continuous, no domain restrictions here. So go ahead and plug in 21 for x. So the cube root of 27, which will be 3. Okay, for part C, this will not be on your quiz. We have a composition. So it says the limit as x approaches 4 of g of f of x. And that's going to be equal to g of the limit as x approaches 4 of f of x. And the limit as x approaches 4 of f of x gave us 21 up above. So we're going to be finding g of 21, which again gave us the cube root of 21 plus 6. cube root of 27. Final answer is 3 for that composition. Again, no compositions on your quiz. All right, there will be trig questions, however, so let's take a look at this next group. So 28 through 36, we have a whole series of trig questions. So for number 28, this is the limit as x approaches pi for tangent x. So let's think about tangent of pi. So tangent of pi, well, if we think about our tangent function, the tangent of pi is just equal to 0. Tangent of 180 degrees, you can take a look at it on the graph, or you can take a look at it as the point -1, 0. Tangent of our function, or tangent of theta, is equal to opposite over adjacent, right? So it's going to be y over x, and that's how I'm coming up with 0, because it's 0 over -1. Okay. All right, and number 30, the limit as x approaches 1 for the sine of pi times x over 2. So let's think about sine of pi times 1 over 2. That's just a fancy way of saying sine of pi over 2. Okay, you can do it a couple different ways. And I know I did the one up above by looking at the points on the unit circle or the coordinate plane. But you may find it easier to look at the trig graphs. So sine function, we know goes from 0, and the pi over 2, we would be at +1. At pi, we'll be back at 0. 3 pi over 2 would be at -1, and then back up to pi. So think about just one cycle of the sine function. Remember that sine is continuous, so the limit exists everywhere. So if we take a look at pi over 2, we're at that point right there, and the limit from the left and from the right is +1. So the limit as x approaches 1 for the sine of pi x over 2 will just be equal to 1. So it's an exact value 1. For 32, we have the limit as x approaches pi for the cosine of 3x. So we're taking a look at the cosine of 3 pi. And again, what about taking a look at the cosine graph? So let's do 2 pi here, and pi, and split each of those in half again. So cosine starts at +1, crosses the x-axis at pi over 2. At pi, we're at -1. 3 pi over 2 back to 0, 2 pi back up to 1. All right, the cosine of 3 pi, well, it's actually going to be similar to what's going on with the cosine of pi, because we know that cosine is going to keep following this path. So between 2 pi and 3 pi, halfway between, it's going to cross the x-axis again, and then at 3 pi, it's going to be back down there at -1. So at every odd multiple of pi in the cosine function, the y value is -1. So its limit will be -1. Okay, so one more trig one on this page, number 34. We're finding the limit as x approaches 5 pi over 3 for cosine x. So let's look at the cosine of 5 pi over 3. All right, if you need to, think of it as being a multiple of 60 degrees, meaning the reference angle is 60, and 5 pi over 3 is equal to 300 degrees. Okay, so rather than looking at the graph of cosine, let's think about using trig exact values here. And I'm doing that for cosine because cosine is continuous, so there are no asymptotes or holes, so we know that we can use trig exact value. Okay, 5 pi over 3, or 300 degrees, is going to put us into quadrant 4. Reference angle is 60, so we'll put 30 up here. Across from the 30 gets 1, and that will be positive because that's on the x-axis, so it's a positive 1 for that side. Across from 60 we get the square root of 3, but it's negative in quadrant 4, and then the hypotenuse is 2. Cosine is adjacent over hypotenuse, so we want to use 1 and the 2. So our limit as x approaches 5 pi over 3 for cosine of x will just be equal to the cosine of 5 pi over 3, which will be 1/2. Okay, so we've got a secant function. We know that secant is undefined in places. It's the reciprocal of cosine, and since cosine is equal to 0 at pi over 2 and 3 pi over 2, secant would have asymptotes at pi over 2 and 3 pi over 2. We don't have to worry about that in this particular case because when we plug in 7, we realize we're finding the secant of 7 pi over 6 and not a multiple of pi over 2. So we're going to be using trig exact value. All right, so we're going to go to our graph, coordinate plane graph. All right, so 7 pi over 6 obviously is a multiple of pi over 6, or 30 degrees. So our reference angle is equal to 30 degrees, and 7 pi over 6 is 210 degrees, because it's 7 times 30. All right, so just in case that helps you. 210, or 7 pi over 6, will put us into quadrant 3. And again, the reference angle is 30. So across from the 30 degrees, that side would have a length of 1, but we're in quadrant 3, so it's negative. Across from 60 degrees would be the square root of 3, but again in quadrant 3 it's negative, and the hypotenuse is 2. All right, we know that cosine of theta is equal to adjacent over hypotenuse, or x over r. So secant of theta has to be equal to r over x, or hypotenuse over adjacent. So hypotenuse would be 2, adjacent would be negative square root of 3. So we're going to start with 2 over negative square root of 3, but that needs to be rationalized. So we need to multiply top and bottom by the square root of 3, and we get negative 2 square root of 3 over 3. Final answer. All right, for the last group of problems in 49 to 57 odd, you need to be careful about just doing direct substitution right away. For instance, on number 49, if you jumped in and you plugged in 5, because we're finding the limit as x approaches 5, watch what happens in here. You would have 5 minus 5, which we know is 0, over 5 squared minus 25, which would also give you 0, because it would be 25 minus 25. So 0 over 0 is called indeterminate form. Meaning we can't determine what it's equal to. So that means that you have to do something algebraic to remove the discontinuity. And in this particular case, we want to factor and reduce to remove the discontinuity. All right, so I'm going to squeeze it in here. So we still keep that limit notation where we're not ready to plug in the 5 because we saw that it ended poorly over here. Keep that numerator, x minus 5. Factor that denominator into x plus 5, x minus 5, because it's the difference of 2 squares. We know we can do that. So we end up with a limit as x approaches 5. Now reduce. That is like actively removing the discontinuity. Okay, keep in mind that we have a 1 in the numerator now. Don't lose that 1. It has to be 1 over x plus 5. Now we've gotten rid of the problem, right? We won't get zeros, or we shouldn't get zeros in the numerator and denominator anymore when we do direct substitution. So we plug in the 5 now. So we have 1 over 5 plus 5, or 1/10, final answer. Okay, so remember, you're never, ever, ever going to give me a 0 over a 0 as a final answer. Doesn't work. That is your signal that there's something algebraic that you can do to remove the discontinuity. Okay, so number 51 is going to be similar, right? We have 2 where factoring and reducing will help us. All right, a little crooked there. All right, again, if you tried plugging in -3, so -3 squared plus -3 minus 6 over -3 squared minus 9, that would give you 9 minus 3 minus 6 over 9 minus 9, which would be 0 over 0. Again, not our answer, right? That's that indeterminate form, but it does signal that we can remove the discontinuity. Right, so we need to do some factoring. The numerator, we have x squared plus x minus 6. That will factor into x plus 3, x minus 2. Check your factoring by multiplying those two binomials back together. The denominator factors into x plus 3, x minus 3. And notice that we get a common factor of x plus 3, which will divide. That leaves us with a limit as x approaches -3 of x minus 2 over x minus 3. Okay, now try your direct substitution. And we get -3 minus 2 over -3 minus 3. That gives us a -5 over -6. And that reduces to 5 over 6. And that's our limit. Okay, number 53, we see something a little bit different. We have square roots in the numerator, but it's really this denominator that's the issue. We're finding the limit as x approaches 0, and we know right away that this will be a problem. Okay, if I plug 0 in there for x, I have 0 in the denominator, and division by 0 is undefined. It would also give me indeterminate form if I plug 0 into the numerator. All right, so what we need to do is multiply by the conjugate of that numerator. So this one is a little bit bigger to begin with. We're going to have the limit as x approaches 0 of the square root of x plus 5 minus the square root of 5 all over x. And we're going to multiply by the square root of x plus 5 plus the square root of 5 over the square root of x plus 5 plus the square root of 5. Again, that's the conjugate. Okay? When we multiply by the conjugate, it's going to get really big and messy, and then we'll clean it up. The square root of x plus 5 times itself will just give us x plus 5. On the outside, we have a positive square root of 5 times the square root of x plus 5. On the inside, we have negative square root of 5 times the square root of x plus 5. And on the end, we have a negative square root of 5 times a positive, so it'll be negative square root of 25. All over, and I don't want you to distribute in the denominator, x times the square root of x plus 5 plus the square root of 5. Okay, so right here, this positive square root of 5 times the square root of x plus 5, and the negative will subtract to 0. And that's why we're multiplying by conjugates. That's always going to happen. Okay, we're left with the limit as x approaches 0, x plus 5, and over here, simplify the square root of 25 to get a minus 5. We're subtracting square root of 25 there. That denominator is still big and crazy, but don't distribute. Okay, this simplifies again to the limit as x approaches 0. Now we just have an x in the numerator because these two subtract to 0. And we have x times the square root of x plus 5 or plus the square root of 5. Okay, those x's will divide. That's removing the discontinuity. And we're left with the limit as x approaches 0 of 1 over the square root of x plus 5 plus the square root of 5. Okay, let me move that up just a little bit. Okay, believe it or not, we're ready to plug in 0 for x. So we have 1 over the square root of 0 plus 5 plus the square root of 5, which gives us 1 over the square root of 5 plus the square root of 5, or 1 over 2 square root of 5. Now, that's not in simplest form because we have a radical in the denominator, so our last step is to multiply by the square root of 5 over the square root of 5 to get the square root of 5 over 10. Because that would be the square root of 5 over 2 square root of 25. And that's how I get square root of 5 over 10. Okay, number 55 is also a problem where if we plugged in 4 for x, it would make that denominator equal to 0 right away. And it would also make that numerator equal to 0. So we're going to jump right in, and I'm going to change this to multiplication, and we're going to multiply by the conjugate. So we want x plus 5, the square root of x plus 5 plus 3 in both the numerator and the denominator. So that'll give us the limit as x approaches 4, the square root of x plus 5 times the square root of x plus 5 will just give us the square root of x plus 5 squared, or just x plus 5. As we said before, with conjugates, the outside and the inside terms will be opposites. They'll add to 0, so I'm not going to write those down. But then the product of the last terms is -9, because we have a -3 times a +3. Okay, in the denominator, don't distribute. Keep it as x minus 4 in parentheses times the square root of x plus 5 plus 3 in its own set of parentheses. So the limit as x approaches 4 of x minus 4 in the numerator once we combine like terms all over x minus 4 times the square root of x plus 5 plus 3. Okay, so that idea of multiplying by the conjugate is so this happens. We're removing the place where this function is discontinuous, and we end up with a limit as x approaches 4 of 1 over the square root of x plus 5 plus 3. So plug in the 4. We have 1 over the square root of 4 plus 5 plus 3, and 1 over the square root of 9 plus 3. So it's 1 over 3 plus 3 is 1 over 6. Okay. All right, for our very last one, this is similar to the first one on the worksheet in that we have a complex fraction. Again, we're finding the limit as x approaches 0, which would make this denominator equal to 0 or undefined. So our idea here is that we want to find the least common denominator, which is 3 plus x times 3, and you could put that 3 out in front. And we're going to multiply both the numerator by that 3 times 3 plus x, and that denominator by 3 times 3 plus x. So we'll have the limit as x approaches 0 of 1 over 3 plus x times that LCD, 3 times 3 plus x over 1, minus 1/3 times that LCD, 3 times 3 plus x all over 1. And in the denominator, just write it as 3x times 3 plus x. Don't distribute. So in the numerator, the 3 plus x will divide out here, and here we're left with just a 3. These 3's divide out, and we're left with minus that quantity, 3 plus x. So keep it in limit notation. So the limit as x approaches 0 of that 3 minus parentheses around the 3 plus x. And in the denominator, don't distribute. I know, I say that a lot. Okay, gonna scoot this all up a little bit. Okay, in that numerator, we want to simplify. So it'll give us the limit as x approaches 0 of 3 minus x, because I'm distributing that negative, all divided by 3x times 3 plus x. So that is going to leave us with a limit as x approaches 0 of negative x over 3x times 3 plus x. Those x's divide. All right, so we have the limit as x approaches 0, negative 1 over 3 times 3 plus x. And finally, we're ready to plug 0 in for x. So it gives us negative 1 over 3 times 3 plus 0, or negative 1/9. And that's it.